I've talked previously about how you can relate the concept of force to the concept of momentum. And from there, you can show that in situations where the net force on a system is zero, that means that there's no change in momentum, which is another way of saying that momentum is conserved. So the momentum before is equal to the momentum after. And that's a convenient way of setting up problems. So I want to make a similar case now when things are rotating. So when you have rotation, if there's going to be a force that supplies rotation, we're going to call that torque. And so in some engineering fields, they call it moment, but it's the same concept. It's a force that supplies rotation. And so there's multiple things you need to consider when it comes to torque. So one, you have to think about what is the actual force being applied, but then you also have to consider how far away from the axis of rotation is that force being applied. As we've talked about with circular motion, for the same angle theta that's being swept out, you can have different arc lengths, i.e. different linear displacements at different distances from the axis of rotation for that very same angle theta that's swept. So if you can imagine, if you sweep by an angle theta and you're close to the axis of rotation, you're not going to cover as much arc length as you would if you were much further away from the axis of rotation. So you have to, with rotational objects, consider not just the force being applied to them, but also how far away that force is. And so sometimes the magnitude of the distance from the center of the rotation to where the force is applied is called the lever arm. And you might have even heard of the term leverage before. So if you can imagine, if you are to have rotation of an object for the same amount of force, so let's say you apply the same amount of force F, if your lever arm gets further and further and further away, right? Let's say like right here is like the axis of rotation. If I apply the same force, say right here, I don't have as much leverage as if I applied the same force right here. Here I would have much more leverage, i.e. I would have a larger lever arm. And so therefore, for the same amount of force here compared to here, I would have more torque out here. Now, another thing with torque that you have to keep in mind is that, so imagine you had like rotation like this. So let's say that we're rotating, and let's say we're going to draw right here like a tangent to the circular rotation. So let's say that the force that's applied actually looks kind of like at an angle compared to that tangent. So you could probably picture there's an angle between my two fingers right now. We need, when it comes to figuring out how much of this force is actually causing rotation, we need to figure out what component of it is in the direction of the tangent to the circular trajectory. Now, the idea behind these physics without equations videos is not to get into the nitty-gritty details of equations. And so I'll leave it to you to look up how you get the component of force that's actually tangent to the circular trajectory, because that's the part that actually supplies rotation. If I, again, like have my tangent, so imagine we're going in a circle, and so I'm just going to draw a point right here that's tangent to the circle. So imagine like here's the axis of rotation, lever arm, and here's the tangent to the circle. If I have a component of force that looks like this, the component that's perpendicular, if you can imagine 90 degrees right there, that's not helping rotation at all. And so you have to figure out, using vector decomposition, to what extent does the force actually have a component that goes tangent to the circular trajectory. That's what's supplying the torque. I'll give you a hint. You're going to see an equation that involves the sine function. And so that's important. You have to not just consider the force in the lever arm, but you also have to consider what component of the force is actually acting tangent to the circular trajectory. Okay, so I also want to make a connection to the inertia idea again. As I've talked about previously, mass is a gauge of inertia, okay? Inertia is a property of matter in which objects at rest, they want to stay at rest. Objects in motion want to keep doing the motion they're doing. Objects, if they have no net forces on them, are just going to continue doing the motion that they're doing. And so an object's resistance to changes in motion is the concept of inertia. And so if you can imagine, an object with more mass is going to be harder to get moving. And once it gets moving, it's going to be harder to change that motion. And so, again, mass is a gauge of inertia. Well, when you get into rotational dynamics, with the idea of torque, supply, and rotation, you're also going to encounter a thing called angular momentum. And to understand this, you have to understand rotational inertia. And so when an object is moving in a linear sense, you can imagine like all the mass is like in my fist as we're moving. All of the mass is moving together. All of the pieces of mass, if you will. If you were to take a mass and think of it as a bunch of mini masses, when they're moving linearly, we assume that all those little pieces of mass are moving with the same velocity. Well, let's say that I have like a cylinder, and let's say that it's rotating like this. And if you can imagine, this cylinder has some mass, but you could also imagine that you could chop it up into a bunch of little mini masses where all the mini masses add up to the total mass. So here's the thing. For the same reason that for some angle theta that is rotated, based upon how far away you are from the axis of rotation, you're going to sweep out more and more arc length for the same angle theta that's swept out. So similarly, like if I had a little mini mass here versus a little mini mass here, when it's rotating, you can imagine that those two little mini masses aren't covering the same distance. Not like the case where we can assume all the little mini masses are covering the same distance. So we have to account for this change. And so the way that we do it is with this concept of moment of inertia. And so moment of inertia is essentially a gauge of how difficult or easy it is to put an object in motion based upon the object's axis of rotation and also how the mass is distributed of that object. And that includes what the shape of the object is. So I'm going to go back to this example again. It's one thing to imagine it rotating like this. It's another thing to imagine it rotating like this. Those are two different axes of rotation. So not to worry, these are not like things we expect you to memorize for every object in the universe. You're going to be able to reference for a given object shape, whether it's a sphere or whether it's a cylinder. You're also going to be able, based on the shape, to look up what the axis of rotation is and whether or not, say, the mass is uniformly distributed. So like if this had mass m, you would imagine that it was chopped up into a bunch of bits that each, had the same amount of little mini masses and they added up to the total mass. Or sometimes objects don't have the mass uniformly distributed. Rather, the mass might be all towards the periphery. Like if you can think of like a wheel doesn't usually have uniform mass distribution. In fact, a lot of the mass is pushed out towards the rim. And so you can look up in tables for different shapes, different axes of rotation, and different distributions of mass, what the moment of inertia is. And the moment of inertia usually has the symbol I. It's the same concept as linear inertia. And again, linear inertia, which is mass, is how hard it is to get something moving and how hard is it to perturb its motion once it's moving. Similarly, moment of inertia is how hard it is to get something rotating. And once it starts rotating, how hard it is to change that rotation. So part of why the distribution of mass is important to consider the moment of inertia. So going back to my cylinder, it's one case when all the mass is uniformly distributed amongst the cylinder, but instead imagine like all the mass was like spushed out to the end. Like imagine all the mass was here and here, like on the ends, and there was very little mass in the middle. Now think to yourself, if I was to apply a force when all of the mass was smushed out towards the periphery of the object, would it be easier or harder to get it rotating? Now the answer in short is that if more and more of the mass is distributed outward where I'm applying the force, it's actually going to be more difficult to get that thing rotating, which is a way of saying that the moment of inertia is greater for that same shape and the same axis of rotation if the mass is distributed more towards the outside. So when I talked about the relationship between linear force and linear momentum, I talked about how when there's no net force, that means that there's no change in momentum, because force can be described as the time rate of change in momentum. And if there's no change in momentum, that means that momentum remains constant, i.e. it is conserved. Similarly, when we're talking about the force that supplies rotation, torque, if there's no net torque on an object, then you can say that there's no time rate of change of angular momentum, which is to say that angular momentum is conserved. Just as I've explained with respect to theta and with respect to omega and with respect to alpha, you can use those rotational analogs to take your linear equations and then have your rotational equations by just making the appropriate substitutions. Similarly, when it comes to force and momentum, you can make the rotational substitutions. So when you talk about inertia linearly, you use mass m. When you're talking about rotation, you use moment of inertia I. So where you see, say, in Newton's second law, force equals mass times acceleration. Well, what are we going to use instead? Well, we know that the acceleration analog in rotation is alpha, so we're certainly going to use alpha there. When we talk about the rotational analog for mass, it's I. So you could also express torque as I times alpha. With respect to momentum, remember linearly, momentum is simply going to be the inertia m times the linear velocity v. Well, we know in the rotational sense, we have the concept of angular velocity omega, so we're going to put omega in for v. And again, when we're in the rotational case, we're going to think of moment of inertia I. And so instead of p equaling mv in the linear sense, we're going to say the angular velocity is going to lead to the angular momentum. And so we're going to define angular momentum as L. And we're going to say L is equal I times omega, right? Just like P equals mv, L equals I times omega. And remember, omega is the angular velocity. So one last thing. So just like when there's no net forces on a system, we can say the momentum is conserved. If there's no net torque on a rotating body, we can say the angular momentum is conserved. And so if any of you have ever seen a figure skater, you're probably likely to have seen that, like, often towards the end of the routine, they will go into a spin on the ice, and they'll start the spin where they have their arms out, and then they'll bring their arms in. And when they bring their arms in, they start rotating more rapidly. That is a perfect example of conservation of angular momentum, because what's happening is that, so imagine that they push their skate into the ice and it originally gives them a torque. And now that ice doesn't have a whole lot of friction, so it's like they're moving around, but the net torque at this point now is zero. And so if the net torque is zero, you can say that the angular momentum isn't changing. So if the angular momentum isn't changing, that means it's constant at different points in the rotation. So what's changing if they have their arms out and then they bring their arms in? What's changing? It's just like when I was talking about this cylinder. You could have a cylinder rotating like this, but it's different if the mass was uniformly spread over it versus if the mass was put out on the ends. And similarly, if your arms are out like this, for the same mass m, you have a greater moment of inertia I than you do like this. So what they're doing is they're changing their moment of inertia. It's greater now, it's less now. And remember, the net torque is zero, so the angular momentum is conserved. So if the angular momentum must remain the same, and you start with a greater moment of inertia I and you make it less, then if angular momentum L is going to be I multiplied by omega, then if it has to remain a constant amount, if you decrease the I, then because the multiplication has to remain the same, I multiplied by omega must remain the same if it's constant. That means that the omega has to go up if I goes down. And so that's why if you change your moment of inertia to something that's larger to something that's smaller, if there's no net torque and angular momentum is conserved, you must now rotate at a more rapid rate.